Today we have the pleasure of introducing our final convergence tests for this course, namely the illustrious ratio test and root test. So by the end of today, we should be able to use each of these tests appropriately to determine whether a series converges or diverges. As always, we have a few motivating examples to show why the tests that we already have are insufficient for our purposes. And the issue is mostly when we have series where the formula for the sequence contains either an nth power, such as 4 to the n, or the real pesky part is if we have an n factorial. N factorial is notoriously resistant to all of the tests that we have so far. Enter ratio test. Ratio test is absolutely perfect for series which contain an n factorial. So let's state the test and then let's see how that test can be applied to series which might contain a factorial term. What we're going to do, the reason why we call this test the ratio test, is we are going to take a ratio, not of one sequence to another, as in limit comparison test. We're going to take the ratio of the series to itself. We're going to take the ratio of a sub n plus 1, the next term in the sequence, to a sub n, the current term in the sequence. If this ratio in magnitude as n goes to infinity is approaching a number which is anything larger than 1, strictly larger than 1, then the series must diverge. If you take the ratio of n plus 1 divided by an, and you take the limit of that as n goes to infinity, if the resulting number is anything greater than 1, your series must diverge. If you take this limit of this ratio and get a number which is smaller than 1, again strictly smaller than 1, then you can conclude that the series converges. And not only that, the series must converge absolutely. So not only does the series converge, but the series still converges if you have an absolute value on the terms in the series. That is, both the sum of ak and the sum of the absolute values of ak converge. Now that is the end of the ratio test. Notice that this test is still locked if the limit of the ratio happens to be exactly equal to 1. This test only covers the cases where the limit is greater than 1 and the limit is less than 1, strictly speaking. So let's note, if the limit of the ratio of the next term to the current term happens to be exactly 1, then the ratio test is still locked and can't be used. So let's get some practice. In the following exercise, we're asked, what does the ratio test imply about convergence/divergence of each of the following series? So the goal is to calculate the limit of a sub n plus 1 divided by an. So we have an in this problem, which is equal to 1 over 2n plus 1. What happens if we consider the very next term in the sequence, a sub n plus 1? Then anywhere there was an n, there is now an n plus 1. So not 2n plus 1, but 2n plus 1 plus 1. Let's simplify this a little bit. If we distribute that 2 and we combine some like terms, a sub n plus 1 has got to be equal to 1 over 2n plus the number 3. So now let's look at a sub n plus 1 over an magnitude. A sub n plus 1 is the fraction with plus 3 in the denominator. A sub n is the fraction with plus 1 in the denominator, which simplifies to 2n plus 1 over 2n plus 3. Next, let's consider what would happen to this 2n plus 1 over 2n plus 3 as n approached infinity. Because this is a rational function of the variable n, begins to approach the ratio of the leading terms 2n to n, which simplifies to absolute value of 1, which is equal to 1. Which means that the limit of the ratio that we obtained is not strictly larger than 1, it's not strictly smaller than 1. So ratio test is still locked. Ratio test is still locked, so in answer to this question, what does the ratio test imply about convergence/divergence? The ratio test implies nothing. In order to determine convergence/divergence of this particular series, we would have to use some other test. For example, it looks like limit comparison might be viable here because it looks like this series is similar to the harmonic series. So I might use a limit comparison to determine convergence/divergence and not ratio test, which would not be appropriate for this particular series. So where does ratio test shine? Ratio test shines when we're dealing with a problem such as 1 over n factorial. In this case, we have a sub n equals 1 over n factorial. And we have a sub n plus 1 equals 1 over n plus 1 factorial. So what we're trying to figure out is the limit as n goes to infinity of a sub n plus 1 divided by a sub n, which simplifies to n factorial divided by n plus 1 factorial. Now let's remember the definition of n factorial, of the factorial of a number. The factorial of a number said, starting from n, count your way all the way down to the number 1, n minus 1, n minus 2, etc., all the way until you reached 3, 2, 1. Then multiply all those numbers together. N plus 1 factorial would be exactly the same thing, except this time you're starting from n plus 1 and you're counting your way down. N plus 1 goes to n minus 1, goes to n minus 2, and count down all the way to 3, 2, 1. Now notice how similar these expressions actually are. N plus 1 factorial and n factorial are almost exactly the same, except n plus 1 factorial just has this singular extra factor of n plus 1 itself. So that means if you divide one of these expressions by the other, if you divide n factorial by n plus 1 factorial, the common factor of n will cancel out, the common factor of n minus 1 will cancel out, the common factor of n minus 2 will cancel out, and so on and so forth, and the only thing that will be left is the singular extra factor of n minus 1 in the denominator. Everything cancels in the numerator, so only 1 remains, and n plus 1 without the factorial is left in the denominator. So let's think about what happens to this quantity as n starts to get large. When n starts to get large, 1 over n plus 1 begins to approach 0. And this number is in fact strictly less than 1. As a result, what can we conclude from the ratio test? The ratio test implies that this series is convergent. The reason why ratio test is so perfect for series containing the n factorial is because of this cancellation that happens right here. The fact that n factorial divided by n plus 1 factorial can always be simplified dramatically to 1 over n plus 1. Let's also see what happens when we apply the ratio test to the following series, where this time we have n factorial in the numerator and we have 4 to the n in the denominator. So a sub n is equal to n factorial over 4 to the nth power. And a sub n plus 1, which I get by adding 1 to all the n's in this formula, is n plus 1 factorial over 4 to the n plus 1. Now let's see what happens if we take the ratio of the next term to the current term. Then that's going to be equal to, in the numerator, n plus 1 factorial over 4 to the n plus 1, and divide that by n factorial over 4 to the nth power. Now do a little fraction arithmetic, do a little rewriting, a little rearranging, and we get n plus 1 factorial over n factorial times 4 to the n over 4 to the n plus 1. Now by exactly the same kind of argument that we used in the previous example, we can dramatically simplify this first quantity, n plus 1 factorial over n factorial. This will simplify so that only the extra n plus 1 in the numerator will survive. Every other factor in that fraction will cancel out. We can also dramatically simplify this 4 to the n divided by 4 to the n plus 1. Compared to the numerator, this denominator simply has one extra factor of 4. I have n factors of 4 in the numerator. I have n plus 1 factors of 4 in the denominator. When I cancel the common factors, all that's left is that spare 4 in the denominator. So what happens to this quantity as n starts to approach infinity? The n plus 1 goes off to infinity, so the entire quantity goes to infinity, and this quote-unquote number is definitely strictly larger than 1. Because we got a number which was strictly larger than 1, we can conclude from the ratio test that the series must diverge. And that's really it. I find the ratio test is usually used appropriately by students. There aren't that many common errors that arise when students use this test. The only thing to look out for is that if the ratio happens to become exactly 1 when you take the limit, you do have to switch to using a different test, because in that case, ratio test will not give you any information about your series. Anything could be happening. Here is our final test for the course, the so-called root test. Ratio test involved a ratio, and sure enough, root test is going to involve a root. So in this setting, we have a series sum of ak, and the quantity that we're going to investigate is still equal to the limit as n goes to infinity. But this time, it's the limit as n goes to infinity of the nth root of the absolute value of a sub n. If this quantity is strictly larger than 1, then the series diverges. But if this quantity is anything that's strictly smaller than 1, then the series converges absolutely. So not only does the original series converge, but if your series happens to be partially negative, the series will still converge even if you turned all the terms into positive terms. Let's get a little bit of exercise. Now, the root test is absolutely perfect in any situation where you have an exponent of n, because an exponent of n and the nth root will cancel each other out, leaving you with something that's generally pretty simple for you to calculate that limit. So for example, here we have 1 over n to the power n. And if we apply an absolute value to that quantity, it's really not going to make much of a difference, because n is always a positive number. So if you take the absolute value of a positive number, nothing changes. So let's hit that with the nth root. The nth root of 1 is always going to simplify to 1. And the nth root of n to the power n, the nth root and the nth power will cancel each other out, leaving just the base behind, the base n. So what happens to this quantity as n goes to infinity? This quantity begins to approach 0 as n gets larger. And this number, 0, is definitely strictly less than 1. Because we obtained a limit that was less than 1 in value, by root test, this series converges. Let's acknowledge the fact that this series is not geometric. In order to have a geometric series, you need to have a constant base. You need to have a common ratio which is equal to a number. But here, both the base, n, and the exponent, n, are non-constant. So this series is not geometric, and in order to tackle something like that, I would almost definitely use the root test in lieu of any other test. I can't think of any other test I would want to use here. Alright, what about our friend 1 over n, the harmonic series? We already know from integral test / p-series test that this series must diverge. But could that conclusion also be made using root test? Now before we get into it, I want to recall from either the very beginning of this course or potentially you studied it back in Calculus 1 or 2, that if you took the quantity n, just n by itself with no exponent, if you took the nth root of n and let n go to infinity, this quantity approaches 1. So, if I look at absolute value of an, and I take the nth root of that, the nth root of 1 is always equal to 1, and the nth root of n approaches 1 as n goes to infinity. So just as in ratio test, when you apply root test and your limit is equal to exactly 1, if the limit is neither strictly less than nor strictly greater than 1, then root test is still locked, neither one of the potential hypotheses were satisfied, and so root test cannot be used to make any conclusions. All right, that concludes the tests that we will be covering in this class. Of course, this is not the full set of all possible tests that have been developed. This is just 10 that are relatively easy to apply, that are relatively broadly useful, that we have decided to focus on because of our time constraints. So here is the complete list of the tests and techniques that we have, and a description of the situations where it's most appropriate to use them. For example, our recently developed alternating series test can only be used on alternating series. Ratio test is great in cases where a sub n plus 1 divided by a sub n is easy to simplify, usually series that have an n factorial in them. And we have root test, which is appropriate if the nth root of your series is easy to simplify. And that usually happens when your formula has an exponent of n in there somewhere. Now there are in fact many situations where you can use more than one test to justify your conclusion about the series. For example, there are situations where you can use direct comparison test, or you could use integral test, depending on your taste. In that situation, you just have to pick whichever test you like the most and use that to support your argument. There will also be situations, perhaps in your life, where none of these 10 tests will be able to make a conclusion about your series. For example, we have no test for the sum of cosine n divided by n. You can go through and you can check each of the tests that we have so far, but none of them are actually applicable to this particular series, cosine n over n. So, faced with a series like that, if you need to determine its convergence/divergence, you'll probably need to head to the broad reaches of the internet to see if there is a theorem which can be applied to this situation. Alright, in summary for today, we introduced ratio and root test, and we practiced applying them.